with the talk
Recording in progress.
with the talk of Vadym Tkachenko devoted to regularity of Birth semi-Markov walks. Please, Vadym.
Just 1 second, so you can hear me and see me.
We just see your photo. Yeah.
Well, because I have my camera from a different device, so maybe you can somehow pin my video from my phone. Well, okay. Now you can see my presentation.
Yes.
So my name is Vadym Tkachenko, and this is a joint work with my supervisor, Andrei Yurievich Pilipenko. Let's begin with introduction. First, consider a birth-death Markov chain, xk, on natural numbers with 0. So it has a reflection at 0, and then from every other state we go either right or left with probabilities p and q, and these probabilities are non-zero and add up to 1. We consider only transient or non-recurrent Markov chains further on. So this means that our process will tend to go to infinity. Our Markov chain will go to infinity as k goes to infinity. And the analytical condition of transience is well known. So xk is transient if and only if such a series converges. And this makes intuitive sense if q and p are constant, then we will have just a geometric series, and it converges if q is less than p, so our process tends to go right. Okay, now I will define a semi-Markov process xt such that it has same transitions on the state space, but it will wait some random time at each state before making a jump. The problem here is that we can have a dependence from the past, so this is a way to overcome this. Let's tau
Vadym, let me ask you. You say we have dependence, so you think that the distribution of these random times is not geometrical, yeah?
Yes. So this is a general case.
So this is not lazy random walk, but
of course
some more general process. Okay.
Yes. So we want these times, waiting times tau I, to be some so non-restrictive positive random variable. So in the case of Markov processes, these waiting times are exponentially distributed, and we want it to be as we wish. So construction of our process. Let tau I be a sequence of positive random variables, and for each tau I, consider a sequence tau ik of its independent copies. And suppose all the sequences and the Markov chain xk are independent of each other. Now we will define random moments of jumps. The first one is 0, and then we define other moments recurrently. by this formula. So I will explain this. So define the next moment of jump. We take a look at the state where our process xk is. And if xk equals I, we take the variable tau I and take its independent copies. So all these tau ik are distributed as tau I, but this way our process will have some kind of renewal property. Then the process xt, defined by this formula, is called semi-Markov process with the embedded Markov chain xk and waiting times tau I. So we can describe a process like this, 0, then t1, t2, and our process takes the values of xk on the intervals, between two consecutive jumps. So when xk jumps, our process jumps and to the same state, and then remains constant for that interval. Okay, now we need to introduce the notion of the moment of explosion. So denote by sigma n the first moment when our process x hits the state n. Definition. Then sigma, which is the limit of sigma n, is called the moment of explosion of the process x. Processes having sigma equal to infinity are regular, otherwise non-regular. There is another way to describe this. In terms of the boundary point infinity. So if sigma is finite, it means that we can reach the point infinity in a finite time. So if we were to model some population with this process, this would mean that our population exploded to infinity in a finite time.
Vadym, can we have an example of such construction where this sigma is finite? When it happens? What is the reason for the explosion at a finite moment of the time?
For example, so I will talk about Markov processes. And this can happen when the waiting times, tau I, become smaller and smaller. And in the Markov case, where we have exponentially distributed variables, let's say with some parameters ai, the average waiting time is 1 over I. And if this ai grows too fast, we spend less and less time, and we can reach like a geometric series, for example. We can reach this infinitely far point. Okay, I will continue. And a small remark that reaching this moment, sigma, means that our process traveled through infinitely many states. So let's formulate the problem. We want to obtain a necessary and sufficient condition of regularity for the constructed semi-Markov process. So we want to know when this sigma is finite and when it is infinite. This problem is well stated in the Markov case due to, for example, Dynkin and Yushkevich. And problems of regularity are also well known in the case of diffusions due to Feller, Ito and McKean, and other classics. So let's take a look at the results of Dynkin and Yushkevich. So it's the same model, but tau I are exponentially distributed. And they obtain a necessary and sufficient condition of regularity in terms of convergence of the series, these two series. And this part here is exactly as we talked. It's just the average waiting time. So if this AI becomes too big and the average time becomes too small, we can reach infinity in a finite time. So I want to briefly talk about the technique used in the Markov case, because it is important for our talk. So first denote MIN, the expectation of a sigma n conditioned on I. So it means that x0 equals I, and sigma n is just the moment of hitting the state n. Then it's not difficult to show that these m satisfy such equations. So starting from the state I, in average, we wait this much time, and then with probability pi, we go right. And because of the Markov property, everything starts afresh, and we get a value of mn, but I plus 1. And the same to the left side. But here we have qi and mi minus 1 n. And a similar equation for the state 0, because there we have a reflection with probability. So it will be a similar equation, but simpler. And this system is solved explicitly. We can write it as a difference of so-called characteristic of x. And here, where this series comes from. From here, it's not difficult to show that convergence of this series is equivalent to sigma having finite expectation, which of course implies that sigma is finite almost surely. So this is how it's done. It's a lot of technical work, but it's a well-known result. Now, going back to the semi-Markov case. The same technique cannot be used in the semi-Markov case because these waiting times, tau I, may not have a finite expectation. So we cannot just write the expectation of hitting time because it consists of waiting times. So the idea is to consider Laplace transform instead of expectation. And maybe we can find some relation. Yes, so the Laplace transform, we can write it for every variable. Okay, let's formulate the main result. So let x be a transient semi-Markov process defined earlier, and sigma be its moment of explosion. Theorem. For every initial distribution of x, we have the following alternative. So the moment of explosion is finite with probability 1, if and only if such series converges. This is a very similar series, but here, instead of having 1 over ai, which is the average time, we have 1 minus the Laplace transform of waiting times. And we can write lambda here, but so it's we just write take this Laplace transform at 1 for to make it simpler, but it's will be the same if we write lambda. And vice versa. Sigma is finite almost surely if this series diverges. First, before proceeding to prove it, or give an idea of proof, I would like to establish a relation to previous results. So, what will this theorem say in the Markov case? In the Markov case, we can calculate the Laplace transform. It looks like this. And taking lambda equal to 1, we have that 1 minus the Laplace transform is equal to 1 over 1 plus AI. Here we take tau I to be exponentially distributed with the parameter AI. Then this series from theorem can be, so we can substitute this into a series, change the order of summation. Now this part here doesn't depend on m, so we pass it outside the second sum, and we arrive at this expression where this part here is equivalent to 1 over AI if AI goes to infinity. And this is some, so we can write it as some quotient dependent on I. So we arrive at the same series as in the Markov case. Now, to make the proof more structured, we first need to do some preliminary work. By the way, if you have any questions or you want to clarify something, please ask me, interrupt me. Yeah, I will try to answer your questions. So let's introduce the conditional Laplace transform of the moment of explosion. We will denote it as Fi. And the same for heating times of some state n from our state space. So once again, we start from the state I, and we are interested in how much time will it take to reach the state n, and we will take the Laplace transform of it, and I will always evaluate it at 1 for simplicity. Then we have this simple result. It says that Fin are non-increasing in n, and the Laplace transform of heating times go to the Laplace transform of the moment of explosion. So the first one is pretty obvious because our process cannot skip states, and if it went to the state n plus 1, it should have passed the state n. So sigma n is less than or equal to sigma n plus 1, and for the Laplace transform, we have the opposite. And the second part is just a consequence of the theorem of monotone convergence. So we have a link between Fi and Fin. Now, the next lemma says how these Laplace transforms are related to the probability we are interested in. So if Fi goes to 1,
Vadim, excuse me, can you go back for the previous slide for this inequality? Why we have this inequality?
Yeah, let me draw a diagram. So we consider some state I, and we take n greater or equal than I, so to the right side. And if we start from the state I, in order to get to the state n plus 1, we will need to first get to the state n, wait some time here, and go to the state n plus 1. So the time it takes to hit n is less than or equal than the time it takes to hit n plus 1.
Actually, this was my question, because as far as I remember the construction, you use several sequences of this, of course, they are independent, equidistributed sequences of these random times, yeah? Or now it is one sequence, because it can happen that you start from I, for example, when I is less than, okay, Fn, I see, this is like okay, oh, I see, now I understand, thank you. Thank you. This is not the situation. I was thinking about different points of starting.
Okay.
Okay.
Thank you. You're welcome. So
For different points of starting, you also will have monotonicity,
Andrei,
but then you have to think about the proof a little bit.
Andrei, why we will have monotonicity? Because you use different sequences of these times.
No, monotonicity for expectations.
Again, so you claim that still we will have monotonicity for expectations.
Yes.
Why?
You can construct, for example,
or maybe you use just conditional expectation first.
yes,
Yeah?
and some
Yeah, okay,
coupling,
okay.
some coupling. You hit another point and then you start afresh.
Yeah, okay. By the way, I thought about this in the beginning of the talk, that we actually can construct stochastic flow based on these rules when we jump over integer points and waiting something. So it is like a discrete stochastic flow. Yeah. Okay. Thank you. Let's go further.
yes. So the lemma says that if Fi goes to 1, then the moment of explosion is finite with probability 1. So it means that we take this state I, we look at the time it takes to hit infinity, and this starting point, we take it further and further to the right. So let me try to prove it, maybe without all the details, but so we will have the feel of it. So first, it's enough to show that starting from every state I, so the conditional probability is finite with probability 1. Well, because we can write this probability as the sum over all conditional probabilities. And of course, if all of them are equal to 1, this one will also equal to 1. The next statement is less obvious. It says that all probabilities are equal. All conditional probabilities are equal. So if we take some states I and j, disordered, we can rewrite the moment of explosion as the sum. So in order for us to hit infinity, first should hit the state j, and then there will be the remaining part. So I can write like this. Sigma is equal to sigma j plus the remaining time, which is sigma minus sigma j. Of course, this sum is less than infinity if and only if each one of these summands is less than or equal to infinity. And because of the way we constructed our process, first of all, these variables are independent. So yeah, because this part is independent of this, and I can write it as probability of sigma j being finite times the probability of this remaining part being finite. And then, because of transients, because our process goes to infinity, this probability is just equal to 1. And because of the Markov property of the embedded Markov chain, this probability here is just equal to pj sigma less than infinity. So because we have the renewal property. Okay. I hope I made it a little bit clearer. And the next point is the following. So Pj is greater or equal than Fj. We need to do a little calculation here. First of all, this probability, we can write this as the expectation of indicator of such event. Then we can estimate it as e to the minus sigma, because this variable here is less than or equal to 1. I need to write this indicator. And now this expectation here, so if sigma is finite, then this variable is just 0. This value is just 0. And we get that is the same as the expectation of minus sigma. Yeah, so this indicator doesn't affect anything because this can be rewritten as a sum of indicators when sigma is less than infinity and sigma is equal to infinity. But the second expectation will be just 0. Okay, and this here is just Fj in our notation. So the Laplace transform of the moment of explosion. So we proved this inequality, and combining second and third property, we get that Pi is equal to all Pj. Then it is equal to the limit of Pj. And this limit is greater than or equal to the limit of Fj. And we supposed that it is 1. So we have that probability is greater than or equal to 1, which of course means that it is equal to 1. Okay. So let me do a little pause. Maybe some questions. Okay, the next point. We found the connection between sigma and Fi. So now we need to establish when Fi goes to 1. And to do this, we examine the Laplace transform of heating times sigma n more closely. Denote by Fi the Laplace transform of waiting times. Then we can write a system of equations which is very similar to the Markov case. Now we have multiplication here instead of addition because we took the Laplace transform. But this equation comes from the same logic. So if we start from the state I, we can rewrite our heating time sigma n as the first moment of jump plus the remaining part. And because of the way we constructed our process, tau and sigma still are independent, and we can rewrite our Laplace transform as a multiple. This expectation is a multiple of expectations. And the first part, if we started from the state j, this waiting time has the distribution tau j. And we denoted it by fj. So fj times the remaining part. Remaining part can be expanded using the fact that we either go right with probability pi or left with probability qi, well, except for the state 0. So we get this system of equations, and we want to somehow solve it or examine it. And it's pretty hard because of this multiplication here. The idea then is to somehow modify the system of equations to make it more solvable. And for that, let's take 1 minus f and 1 minus phi, and denoted by f capital and phi capital. So let's take a look at our system once again. And here how it transforms in our new terms. You can say that it became worse, and I can agree with you. But now we have this nice part here. And so it looks kind of more linear. It is, of course, not, because here we have f inside. But the idea then is to simplify this system of equations and get rid of part here. And maybe if we can solve this equation, we can draw some conclusions about the previous one. And it is, of course, the case, because we saw such systems already in the Markov case. But there we had the average of the waiting times, 1 over AI. So now we can solve the system and find a way to compare its solution to the solution of the original system. And well, of course, Pi and Qi are our probabilities. F is just 1 minus the Laplace transform of a positive random variable. So this Fi is less than or equal than 1. and greater or equal than 0. So this whole part here it's of course less than or equal to 1. Yeah, sorry. So it is convenient to consider a general system of equation of such form, where AI are some non-negative numbers. And this system of equations has a probabilistic interpretation. We travel on the state space between 0 and n, starting from the state I, and at each state I, we get a profit of a I. And we do this until we hit the state n. So travel, we add some profit, and do this until we hit n. Then y is just the total profit and we hit n. And from this interpretation,
Vadim, not total profit, but expectation of total profit.
Oh, I'm sorry, of course. Yeah, total expected profit. Thank you. And from this interpretation, we get a solution for this system in the following form, where this kappa n is so it's just a number so xk is the embedded Markov chain of the process x, and this is the first number when this embedded Markov chain hits n. And the explanation for this formula is as I described. So we take a look at the state where our process is and add profit until we hit n. And from this lemma follows a very important corollary, or another lemma. Well, if we have a similar system for y tilde, but instead of a I, we have some b here, and b is less than or equal than I, then the solution is also less than or equal than the previous one. So in our interpretation, it becomes obvious, yeah, we get less profit at each stage, then our total profit is will be less. And the last thing I want to note here is that this formula for solution can be applied to our original systems, where these profit coefficients will be like this. So this lemma applies to our original system of equations. But here, like AI will be equal to this part. And so it will kind of depend on the, not only on the state we are in, but also on the neighboring states. Okay. The last result gives us the explicit formula for the solution of our simplified system. And it's just the formula from the Markov case. We can rewrite it in a more familiar fashion. And this is exactly the characteristic from the Markov case. But here we have AI instead of 1 over AI, the average waiting time. So I hope I didn't lost you. Anyway, let's make a short summary of our preliminary work. So what did we do? We introduced the Laplace transform of the moment of explosion and waiting times. Then we noted that Fin are non-increasing in n, and Fin goes to Fi. We showed that if Fi goes to 1, then sigma is finite almost surely. Then we found a system of equations for Fin, for the Laplace transform of the heating times. Then we modified and simplified it. We found a solution and found a way to compare these solutions, and got an explicit formula for the solution of our simplified system. This explicit formula comes from the theory of Markov processes. So now we are ready to try to prove the theory. So let us prove that from this convergence follows that sigma is finite. And in our notation, this is just 1 minus the Laplace transform of the waiting time, and we denoted it by phi. And later we denoted 1 minus phi by phi I large. This series can be written as S infinity of phi. So by this we denote this series with phi I here. Okay, so suppose that this series is finite. We know that it's enough to show that Fi, the Laplace transform of the moment of explosion, goes to 1. From a comparison lemma, we get that 1 minus Fin, which is by definition equal to, by definition of Fin, is equal to Fin. And now here is what I was talking about. Let me recall the equation for Fin and on the middle part of it. So it looks like this: Fi 1 minus Pi F I plus 1n minus Q I F I minus 1n plus Pi F I plus 1n plus Qi F I minus 1n. Okay, and the equation for J is without this part here. And as I was mentioning earlier, this part is, of course, less than or equal than 1. So here we can use our comparison lemma, as this is our profit that we get each time. Okay, and for the equation without this part, we have an explicit formula. And here it is. Now, passing to the limit, we obtain the following inequality. So fin goes to fi, and Sn goes to S infinity. And we supposed that it is finite. And now, of course, if this is finite, we can see that this goes to 0 when I goes to infinity, because this goes to 0. And this means that fi goes to 1, and our lemma applies, and we have that sigma is finite almost sure. The other side, suppose that the moment of explosion is finite almost surely, and we want to show that this series is convergent. First of all, this inequality is true in all cases. Let me draw a picture. So we have state infinity, 0, and some state I, and state n. And this inequality says that, so it comes from the fact that if we start from any state I and count the time until we hit n, this time is, of course, smaller than the time it takes to hit n from the state 0, which is smaller than it takes to hit infinity from 0. So f0 is like the extreme case. It's the biggest time. And then if this probability is 1, the Laplace transform is positive. So it cannot be 0. For this, it's enough to have that actually to know that this probability is positive. Okay, then what we can do? We can consider a new system of equations with this delta here. The idea is to estimate our solution from another side. Because now if I write this part for corresponding to the equation for f, plus 1 I minus 1 and qi. Then it is equal to fi 1 minus. And I recall that f big is just 1 minus f small. And if I write this, I will have 1 minus pi minus qi plus pi f small plus qi this vanishes. Here we have f small, which is greater than or equal to delta for all indices. So this can be estimated as fi times pi delta plus qi delta, which is of course equal to fi delta. I'm sorry, delta. This means that our comparison lemma applies here. And we get that the solution fin is greater or equal than h. But this equations for h, we know the solution for this system because it's the same as it was for J, but now only multiplied by delta. And the formula is the following. It's delta times the difference of this kind of characteristic. Then we can rewrite this difference and estimate it from above by 1 over delta. And these numbers are always less than or equal than 1. So we have our estimate for the difference of our sums, which of course implies that partial sums are bounded and the series is convergent. And this finishes the proof of the first statement of our theory. And the second statement is about sigma being finite, being infinite, I'm sorry. I will probably skip, but I will only talk about one part of it. So if we assume that sigma is infinite, with probability 1, and suppose that our series, or even if we suppose that this probability is positive, and if we suppose that our series converges, we will immediately get a contradiction, because we know that if the series is convergent, this probability should be equal to 0. Okay, and I will skip the small technical remaining part, and rather talk about some examples. And the first example is homogeneous case when transitional probabilities are the same. So pi equals to some p and qi equals to some q. And in order for our process to be transient, we have to have p greater than q. In this case, this part here will be just some power of q over p. And well, almost. And this can be summed as a geometric series, and we will arrive at the following series, just one series, with 1 minus the Laplace transform. And the second example is when we have specific waiting times. So let tau I be distributed as some positive number ai times tau, where tau has a alpha stable distribution. In this case, its Laplace transform can be calculated, and it looks like this, where c is some constant, so it's e to the minus c ai to the power alpha. And if we are to write 1 minus the Laplace transform, we see that it is equivalent to c times ai to the power alpha, as this number, this ai, go to 0. And we can write a similar series in this case. And for homogeneous case, we will get some simple relation between alpha. What if we suppose that ai are powers of some fixed number? So that will be the end of my talk. Here are some references. So this is the main book of Dymkin and Yushkevich with the description of a Markov case. Very nice book. And so a book of Feller about diffusion processes. And the same, so diffusion processes by Ito and McKean. And just a book about Markov chains, about recurrency and transients and so on. That's it. Thank you very much.
Thank you for your interesting talk. Maybe somebody have questions or comments, please.
Maybe I would like to make some comments on this
Mhm,
talk.
mhm.
So when we consider one-dimensional diffusion, there is complete characterization of a point, like entrance point, exit point, natural boundary for one-dimensional diffusion, or regular boundary. And there are the following possibilities. For example, with certain, sometimes the point may be not reachable at all. Sometimes you can reach the point with positive probability. Sometimes diffusion, there is a possibility to construct a diffusion process that hits a point and exit a point. Or sometimes you can exit from a point but not enter again. For example, sometimes Bessel processes for large parameters, Bessel process never hits 0. For certain parameters, you can enter 0 and exit. And sometimes if you come to 0, you cannot exit. So there is no there is no Markov process that behave as a Bessel process inside 0 infinity. 0 is not included. And that can exit from 0. And my question to Vadym was, describe all of this situation for semi-Markov chains. Semi-Markov chains. And the first question was, when infinity is reachable in finite time. And we have complete characterization. And we see, well, for one-dimensional diffusion, everything can be described in terms of scale function and speed measure. And scale function for random walk for semi-Markov process is inherited by scale of initial Markov chain. And we see that analog of speed measure is constructed in terms not of expectations, but in terms of 1 minus Laplace transform. And we hope that we will find we will describe all possibilities for the point plus infinity. So is it reachable in finite time? Can you reach infinity and exit from infinity? Or is it possible to start from infinity and enter integers and so on? Well, and Vadym also had some calculations for this reflection for infinity, and I hope that he will finish this work soon.
Okay, thank you for the comment. I also have some historical comment. I think that Valentin Mikhailovich Shorenkov has a nice preprint, which is named process with semi-Markov randomness. And he did a lot about such kind of processes where we have exactly to stay with any motion some random times and jump and so on. Jump with some kernel. So at least I think it can be, it must be noted in your work because it is very, very related. For example, your equations with this phi, this is exactly equations for like.
Yes, sure.
Yeah, exactly. Yeah, you know.
Yeah, we use like renewing point, and that's all. And it was okay. The problem was to find necessary and sufficient conditions.
Yes,
so
I see.
This was difficult.
I don't say that it is done already, but I say that some similar considerations were done, so it must be noted. This is the first one. Second one is about the construction of the flow. Maybe you remember this picture, which already arise a lot of times at our seminar related to the approximation of a radial flow from the gluing together simple random walks when we have the walk over integer points, and at every integer point we have just random direction. Yeah. And then when two particles hit one state, then they move together. So I think the same construction can be done here. And it is interesting to see what the flow even on the discrete stage space you obtain, and something about scaling.
But you see, the times are not exponential. So the amount of time that you spend in a point depends on the past.
Yes, I see. I don't claim that it will be something which we already have. So it will be interesting to see what happens when we scale this discrete flow and so on. So I think that it will be interesting. Yeah, this is the first. The second and the last one is this book of Dynkin Yushkevich, the same as in Russian, Теорема и задачи about. Yeah?
Yes.
This is okay because I
they have two. They have two books, at least two. Okay.
окей.
Теория вероятности и марковские процессы, кажется.
Нет, есть, называется...
Управляемые марковские
Это
процессы.
одна, а вторая
Теорема и задача
теорема и
процесса
задача
Маркова.
о процессах Маркова. Okay, so if there are no other questions or comments, then Vadim, thank you for interesting talk, and Georgi will say us what about next seminar.
Next speaker will be Maria Belazerova.
Okay, good. So we have some qualitative properties of equationless interaction. Okay, then for today that's all. Thank you very much. See you next week. Bye.
Thank you. Bye.
Thank you. Bye.